next speaker. So next speaker is Professor Dohun from Seoul National University, and he's going to talk about coherent manipulation of a strongly correlated electron state in gallium arsenide quantum dot.
Thanks. I'd like to first thank the organizers for inviting me here. Today, what I'd like to talk about is coherent manipulation of electron spin states, multi-electron spin states in gallium arsenide. The picture you are seeing here is one of our examples of coherent interference that is made by free electron spins inside the gallium arsenide quantum dot. And throughout the talk, I will explain how we make this kind of system and how we measure these interference patterns. So I'd like to first acknowledge my students. This is really a strong collaboration between experts in device fabrication and quantum measurements and numerical simulations. So after I explain a review, a little bit of quantum dot-based quantum computing, I will then move on to explaining 3-electron hybrid qubits that Michelle just mentioned in her talk. And then I will move on to our main observation today. Not only we are seeing the hybrid qubits that is known before our experiment, what we see is a little bit of weird phenomena, and I will explain those phenomena in this talk. So I will briefly recap what Michelle just talked about, and I will focus more on gate-defined quantum dot rather than donor-based quantum computing. The picture you are seeing here is a basic structure of so-called overlaid gate structure of a gate-defined quantum dot. We start with high mobility semiconductors like silicon, gallium arsenide, or germanium. We make nanogates on top of the surface. So you are seeing examples of silicon devices made in Wisconsin, USA, and silicon quantum dot devices in my lab, and as well as gallium arsenide quantum dot devices. As Michelle said, silicon quantum computing is really boosting up nowadays, and my lab also can do kind of coherent manipulation on silicon quantum dot. We recently achieved device fabrication and initial dot formation. But for coherent manipulation, we are still in gallium arsenide world, and we hope that we can catch up these silicon nice results very soon. But the point here is that we start with free electrons that is living at the interface, and then use these nanogates to make an electric potential to confine electrons in a well-confined area. And also we flow a current nearby the quantum dot, and what we measure always is whether this electron inside the quantum dot is present or absent or tunneled out to the reservoir. So I will explain by this simple equation. One might think that how can you measure this very small change of charge? It is only one charge difference, but the point here is that the capacitance in nano devices are also very small, and if you divide these two numbers, you can get a non-negligible, still non-negligible voltage effect that is affecting the flowing current nearby the quantum dot. So for example, if you make the dot potential relatively lower than the Fermi level, then mostly in most time, the dot is occupied by one electron, but sometimes electron can tunnel out to the reservoir. So you can see these spikes, and these spikes represent the tunneling out events, and you can basically measure tunneling events in real time. And on the other case, when you make an energy level to very close to the Fermi level, then the tunneling is very freely allowed, and you can see it is fluctuating two-level sensor signal. And the opposite case is the same. When you make an energy level higher than the Fermi level, mostly electrons is outside the quantum dot, and you can often see tunneling in events. And these kind of transition happens all around the Fermi level of the reservoir within a few kBt energy scale. So this is how we measure various quantum states inside the quantum dot. For example, if you want to distinguish spin down or versus spin up, what you do is apply a magnetic field and put your Fermi level in between these two level system. Because only if electron occupies the excited state, then this electron can tunnel out very quickly, giving my sensor signal change. But when you wait long enough, the electron from the reservoir reoccupies the quantum dot to the ground state, so my sensor signal is recovered. Whereas if the state is originally ground state, nothing happens. And this is what exactly Michelle just explained in her slides. And we can do also the very similar, actually the exactly same experiment in gate-defined quantum dot experiment as well. Not only single electron spin states, we can distinguish two electron spin states. For example, singlet versus triplet. Because triplet states, when they occupy the same dot, one electron should occupy the higher orbitals, and this electron can tunnel out, giving my sensor signal. And depending whether there is a pulse or not, we can distinguish 0 versus 1 state. So basically what we are distinguishing is if the qubit state is ground or one of the excited states. And this is called single shot based qubit readout in semiconductor research field. Coherent manipulation is mainly done by shooting microwaves. But along with the microwaves in gate-defined quantum dot, because we are shaping our potential, mimicking the atomic potential, that's why this is called artificial atoms. And because we have these voltage knobs, when you have more than one quantum dot, you can adjust this voltage difference, VL minus VR, to make various transitions between ground states. For example, like this. And the point here is that there is always a crossing point when two or more energy states becomes degenerate, but almost always there is a tunneling, and this crossing becomes actually the anti-crossing and make an energy gap here. So in terms of this control knob, VL minus VR, I will spend a few minutes to explain very briefly, very basic about the quantum dot-based quantum computing. We have basically two electrons in 1-1 situation or 2-0 state situation, and we have various energy splitting like this. The small energy splitting is given by external magnetic field, but compared to 1-1 case, 2-0 state has one more ingredient that is called singlet triplet splitting, and that occurs because of the Pauli exclusion principle. When two electrons want to occupy the same dot, because of the Pauli principle, one electron should occupy the higher orbital, and that's the origin of this big energy splitting. And if you remember that the tunneling basically or nominally does not change the electron spin, we can only select the same spin states. And when you ignore all the other states, you have a simple two-level system. Here I show, I focus on these 4 energy levels that corresponds exactly these 4 energy levels. This is a down, 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 up, down, and up state. And most importantly, what you can notice is that the third energy level is a little bit bended, whereas the other energy levels are perfectly parallel. And going back to this slide, this explains the origin, and this is because there is a tunneling and making this crossing the anti-crossing, and that's the origin of this a little bit of bending. And this a little bit of bending is called exchange interaction. And this exchange interaction is the key to realize the qubit-qubit or spin-to-spin coupling in gate-based quantum dot devices. I will briefly go through 2-qubit experiment with this slide. We start with a down-down situation with product state 2-qubit situation. We apply a microwave or Hadamard gate to make equal superposition of 2-qubit states. And crucially, what we do is adjust the voltage difference between the dots, sweeping this area back and forth. And if you remember, this area represents the phase change or phase difference between relevant energy levels. Because the third energy level is bended a little bit, we can make the red area 2 pi phase shift, whereas the blue area pi phase shift. That means that the target qubit state becomes a minus phase compared to only when the control qubit state is down. And this is called control Z gate. And after that, when you apply Hadamard gate again to the target qubit, what you can get is finally entangled state. So with this kind of sequence, the take-home message is in quantum computing, single qubit gate is nominally produced by Rabi oscillation or a microwave excitation, whereas a 2-qubit gate is nowadays most commonly done by exchange interaction-based controlled phase by pulsing these voltages for some time. With this basic concept, I briefly show the recent developments of number of qubit or number of entangled qubits in quantum dot devices. It all started with a gallium arsenide demonstration, but as soon as a single qubit operation was done in silicon, the research field is really boosting up. Now we are talking about 4-qubit GHZ state generation, entangled state generation in germanium, as well as 6-qubit processor operation in silicon in QTAP. And most recently, companies like Intel Corporation has got into the field, and they are making their own spin qubit devices with CMOS process. So with these beautiful developments, today I'd like to move on to more complicated spin qubit type. And for this experiment, I show my device, which is a gallium arsenide gate-defined quantum dot, and I will focus on these 2 quantum dots, but the number of electrons is actually 3. So 3 electrons in gallium arsenide quantum dots. We can have 2-1 or 1-2 configuration. Compared to 2 electron case, it becomes more and more complicated, of course, because we have 3 electrons, we can 3 spin states, we can have 8 combination of these energy levels, both in 1-2 and 2-1 configuration. But the thing is that energy levels are very symmetric. As I told you that there is a big energy splitting, singlet triplet splitting. And if the dot is very symmetric, we can have very symmetric energy splitting here. And also, if you remember the tunneling selection rule and ignore all the other spin states, focusing only on spin half states and focusing on the lower branch, we can still define 2-level systems. And basically what I have done while I was in USA with a Wisconsin group was to make a two-level system out of 3 electrons in silicon germanium material system. And this is called hybrid qubit. And basically what hybrid means here is this hybrid between spin and charge state. You can see that here it is a spin regime where energy levels are parallel each other, very robust to the charge fluctuation. But you can also see this is a charge qubit regime. It enables very fast electric manipulation as well as spin protection from charge fluctuation. So remember this energy splitting, and I will today I will explain what is strange in our observation. Basically, what we have measured already experimentally is that right quantum dot has a singular triplet splitting of this amount of 0.4 millieV. And basically, what you expect that is that energy difference should look like this if the quantum dots are very symmetric. But what we find is that on the left-hand side, when we measure this energy splitting, actually, you get 10 times smaller energy splitting. Of course, if the quantum dot size are a little bit different, this orbital energy splitting can be a little bit different. But if you just ascribe to the quantum dot size, it means that left quantum dot is about 10 times larger than right quantum dot. And it is really weird. If you consider the lithographic size of the quantum dot you have. What we find that is this energy level is actually very tunable. If you make a little bit of potential shaping, then this energy level sometimes becomes 10 gigahertz. It can become 3 gigahertz, all the way down to 1 gigahertz. And in this regime, if you again only ascribe this origin to the quantum dot size, it means that left quantum dot is 100 times larger than right quantum dot. And this simply doesn't make sense. So anyway, I will explain the origin in a later slide, but I will first explain that this energy level, because it is a very small and very convenient microwave regime, 1 or 2 gigahertz, we can simply apply microwaves and coherently manipulate these states. Interpreting these energy levels as hybrid qubit, 3 electron spin states, we can see that even in gallium arsenide is notorious that to have nuclear spins and all the spin noise, but you can see that we can still do pretty decent Rabi oscillation measurement. Number of oscillation is more than 20, and you can have different time scales of coherence times, and it is still in the long ensemble average time limit. It is still limited by nuclear field or hyperfine interaction, but you can see that we can do a coherent manipulation even in gallium arsenide with single shot measurement capability. So qubit demonstration, it is okay, but my main point is that it was really strange to have this small qubit splitting, and I will explain basically the origin of this small energy splitting. And this is basically the orbital quenching, and we call this Wigner molecule formation. So Wigner crystal is electron localization phenomena due to strong electron-electron correlation. That is a strong Coulomb repulsion in very low density limit. And the parameter that describes the importance of the electron correlation is called Wigner parameter. And Wigner localization can happen in confined system like quantum dot. And when it happens in this confined system, we call it Wigner molecule. Actually, in gallium arsenide, when you make a conventional quantum dot, this number is order of 1. So it is not negligible, but electron-electron interaction cannot be said to be dominant. But the point here is that confinement potential is shaped by the gate voltages, and you can actually tune your importance of electron-electron interaction. That's the Wigner parameter. So we have checked that if our gate geometry is so special that allows this high Wigner parameter. So what we find is that contrary to our expectation, actually the dot forms very elliptically inside the gate geometry. We have checked that with the electrostatic simulation, our quantum dot has a very elongated quantum dot size, as well as very shallow quantum confinement potential. So using this quantum dot size and potential shape, two-dimensional shape, we have actually done full configuration interaction calculation, which is one of the first principal calculation methods, perturbative methods, that we start with ground state, Hartree-Fock approximated ground state, including the singly excited or doubly excited, multiply excited orbitals. We write our many-body ground state. So this is one of the actually the calculation that if the quantum computer is developed that can do better than a classical computer. But the thing is that right now we don't have any fully functional quantum computer, so we had to run this calculation with our classical computer. But it is 2-electron system, 2 or 3 electron system. We can manageably do this kind of FCI calculation, and calculation tells us that it is indeed because of electron correlation. For example, if we turn off our electron-electron interaction, as we consistent to our experimental result, the orbital splitting is tens of or even 100 gigahertz. Whereas if you turn on our interaction, we really find that this orbital splitting is quenched down to 1 gigahertz. And as you see, the wave function of inside the quantum dot, even the ground state is highly, nodal, highly localized inside the quantum dot. So we basically think that we have found a Wigner localization or Wigner molecule formation in one of our quantum dots. Of course, it is accidental. It was accidental discovery, but we think that right now we are really seeing the Wigner molecule formation. So going back to our previous diagram, what we are seeing is that this energy level in left quantum dot is really small, cramped due to electron-electron interaction. And instead of this diagram, we are seeing this kind of diagram. And we were measuring the energy levels here. So far, so good. We have found the origin of this extremely small energy splitting, but we still have the kind of phenomena, experimentally found phenomena that we cannot possibly explain up to now, and this is called magnetospectroscopy. What we have done is investigating this energy splitting as a function of magnetic field, and it was really weird. As a function of magnetic field, at some field, it splits into 4, but as you ramp down your magnetic field back to 0 again, it goes to different track and then quenched at lower field. In the minus direction, this kind of phenomena happens again. When you go back, it becomes to different track and then quenched at lower level. It is hysteric phase transition, and we don't know, we don't have any idea right now, not yet, how to explain this kind of weird phenomena. Maybe we are seeing the phase transition inside the Wigner molecule. We don't know. We have big question mark here. So I apologize that I end my talk with big question mark, but that is right now our stage. What we at least know right now is that because on the left quantum dot, the orbital level is quenched due to electron-electron interaction, we can actually use this interface between strongly correlated molecule versus non-strongly correlated molecule and initialize our qubit state in our big splitting here, go to here and coherently manipulating, and then go back to non-correlated regime and do the single shot readout. We think that we can actually, and if we can engineer this kind of phenomena, strong correlation inside the multiply occupied quantum dot, we can have multiple opportunities that can be related to quantum information processing. As I showed you in the last slides, because these energy levels are very quenched and have a very favorable energy splitting, the coherent manipulation is very, very good. Whereas in the non-strongly correlated quantum dot, we can have large splitting that facilitates the single shot readout. So this was our idea, but so far, I showed just one example that we have accidentally found this kind of phenomena, but we are on our way to engineer this kind of orbital quenching. So I think right now it's good time to stop here, and thank you for your attention.
Okay, thank you very much for the nice one. So now we are open for some question. I don't see any question from the chatting window. So there may be question from the people in the offline place. So while we are waiting, I just want to give you one question. Sure. If I don't know if I understand correctly, but for the spin to charge conversion and for the readout, it looks like you need to have at least one electron remaining in one quantum well. Is this correct?
In a quantum well?
Yes.
In the reservoir?
In the quantum, so for example, in two quantum, you have a double quantum well.
Yeah.
And for the readout, so you have now two correlated electrons and one electron from just a singlet. No.
Oh,
maybe it's
the readout in this case is performed as I showed you. Let me go back here. Yeah, in this slide, what we mean is that this is a situation in 1-2 situation. So what we are reading out is spin state of the right quantum dot. So one quantum dot is remaining in the left quantum dot. I mean, one electron is remaining in the left quantum dot, and we are distinguishing these two electron states on the right quantum dot, whether it is singlet or triplet.
Okay. Okay, thanks.
Yeah.
So since there's there's a question from Michelle.
Yeah, look, it's just such an amazing result. Can you go back to your previous slide? That one. So Dohun, yeah, so just give me some sense of what that is, because it is quite striking and it's reproducible. So
yeah, I mean, personally, this is the first time in my lifetime to see this kind of magnetic spectroscopy. I mean,
yeah.
So there's I mean, if I conjecture this as a phase transition that happens along this field, it has kind of a supercooling, or if I think of it as a first order phase transition, we can think of it as a solid state becomes liquid-like state, and then when we cool down to the solid state, it remains as a liquid state for some time, and then quench to the solid state. That kind of picture I have in mind, but
It's
I
very,
don't know any other idea.
it's very, very intriguing. Anyway, look, it's fantastic. So thank you.
Thanks.
Okay, so if there's no more question, let's thank our speakers again.